Okay, then we're starting.
So just a reminder, I think you guys know this, but next Tuesday we do not have class because it's a Monday schedule. So on Monday, President's Day or something like that. So the college is actually closed completely on Monday. So you don't have any classes then either. But then Tuesday will follow a Monday schedule, so we will not be here. So I won't be seeing you guys until Wednesday. Hopefully I can use that time to really rest up and beat this thing. But today we're not going to do anything too crazy. We're going to actually look over some limits and talk about indeterminate forms. You may or may not have done this in Calc 1, it depends. If you haven't done exponentials and logarithms in Calc 1, then you probably didn't touch on this, but otherwise it might be something you've seen before. I just wanted to remind you about it. And so it's called Indeterminate Forms and L'Hopital's rules. This is 6.8. This refers to just forms that we cannot really determine right away just by looking at them. You have to be very careful and be very delicate when you're working around them. And they show up when dealing with limits. So these are, there are certain forms that you won't be able to actually determine what they are. Infinity over infinity is an important form. Or 0 over 0. There are also others like infinity minus infinity, or 1 to the infinity, or 0 to the 0, or I think I got all of them. Well, infinity to the 0 is another form. The idea, especially, is there are many cases in which when you're dealing with 0, like 0 over 0, for example, that's bad. It seems to not be determinate. But there are cases like these that you would have limits that do like this, but you could simplify them to actually kill the problem. So before, we could avoid some of these by simplifying. Right, so for example, you could get something like, okay, what is the limit as x approaches 1 of 2x squared minus 2 over x minus 1, or something similar to that. Now, you'll notice that if you actually plug in x equals 1, this kind of approaches 0 over 0, which was bad. You couldn't actually tell what that number would be. And so one thing you could actually do is you could just start to simplify. You'll realize that you could actually factor out a common 2 here, and you could notice that that's the difference of squares. And so at some point you could actually now plug in x equals 1, so that would be 2, so that you will get the answer 4, right? So in the beginning it was something that's crazy like 0 over 0, but you can actually use algebra and manipulate things to get to a reasonable answer. The way that limits were defined made this very plausible. But what about things like if you had the limit as x approaches infinity of something like e to the x over x? right? Then that simplification thing is not something that is available to you anymore. You can't really factor and simplify here. And you really need to know how the functions behave in relation to each other, or you'll need to know how the graph looks, which is, even with all the graphing skills that you picked up in Calc 1, graphing that is still going to be pretty annoying. And so you can't really deal with that as well. And the fact that there are different sizes to infinity, so you're not sure if infinity divided by infinity, if this one's bigger than that one, or vice versa, and that's why subtraction is kind of weird. But yeah, so there are times when the simplifying idea does not work, and you have more complicated functions, and so we need actually something better. And one way to actually do these one option we will now have, or it's possible that you did it in Calc 1, but I'm not sure. Is L'Hopital's rule. Named after a French mathematician, L'Hopital. So the rule says the following. It deals with two of these indeterminate forms, the ones that are in division. Okay, so it actually doesn't apply to any of these, but we'll realize that there will be ways that we can rewrite these guys to kind of fit into these forms here. So suppose we want to compute the limit as x approaches c of one function divided by another. Where this limit approaches 0 over 0 or infinity over infinity, plus or minus doesn't matter. Then turns out that the limit of this guy is actually equal to the limit of the derivatives of each of these functions. And this is called L'Hopital's rule. So there are really two main situations in which you can apply it. Your limit has to be approaching 0 over 0 or infinity over infinity. So none of these other forms are actually used here. So you have to have one of these two forms, and it turns out that the limit of the original function that you cared about will be the limit of the derivatives. And this is something that you can actually keep going, right? So maybe the derivatives themselves also give you that form. You can actually take derivatives again. And so that will be equal to this, which you know is equal to that, and you can actually keep breaking this down. And as long as you keep getting one of these two forms, you can keep applying L'Hopital's rule, and eventually the goal is, eventually you want to be able to get to a point where you can actually take the limit, and it will be equal to the original limit. So the proof of this is a little bit hairy, so I'm not going to prove that for you, but we're just going to be able to use it. So I just want to give you a few examples where we're using it in various situations to find limits. And later on, when we actually do series, we'll look at another way to find limits. That would come up. So something besides that also. There are some limits that I do expect you to remember. So there are a bunch of special trig limits. So for example, if you have the limit as x approaches 0 sine x over x, or the limit as x approaches 0 tan x over x, or the limit as x approaches 0, 1 minus cosine x over x. Do you guys remember what these guys were? What is this guy? It's actually 1. Which, by the way, because it's 1, you can't actually take reciprocals, so it's actually equal to the other way around. This one? It'll also give you 1, because you can kind of write the tangent as sine divided by cosine. You can factor off the cosine. But as cosine goes to 0, it just gives you 1, so the cosine doesn't really affect the limit. And you still kind of get back to this sine x over x. So that also you can think of as working in the other way. This guy though, this guy actually goes to 0, so it doesn't have a reciprocal form, but you could have either a plus or a minus happening to this, and that would give you 0. By the way, if you ever forget these guys, you could derive these using L'Hopital's rule. But it's good to know them off the top of your head, because there will be situations where it's just easy. Once you see it popping out at you, you don't want to actually overuse L'Hopital's rule too much, because you might get confused. But you can always use these guys to your advantage. Those are things I expect you to know and be able to apply. So let's actually look at some examples here. So let's look at an example where we have the form 0 times infinity. For example, let's look at the limit as x approaches 0 from the right of x times ln x. Now because we know how ln looks, we can realize that this will approach 0 times negative infinity, right? Because the ln, remember the ln graph looks like this. So if you're approaching 0 from the right, it's going down to negative infinity, and obviously x itself is going to 0. So we have this form where we have 0 times infinity. It's not always clear what this guy is, because you might think 0 times anything should be 0, but infinity times anything should be infinity. So what is 0 times infinity? It's kind of like, you know, the immovable object meets the unstoppable force, so you're kind of not sure which one's going to win out. But the trick here is, the first you can do a little bit of simplification. Since our limit, we're not specifically at 0, we're just approaching 0, we can actually rewrite this in a certain way. So I could rewrite this to look like something like this. Rewrite the x to look like a 1 over x, right? So now that's my top function, and this is my bottom function. And why would I do that? Well, now look at what the limit approaches. What would it approach now? Infinity would be on the top. What about this 1 over x as x approaches 0 from the right? It's also infinity, right? So remember that our 1 over x, this is y equals 1 over x, is that guy. As you're approaching 0 from the right, that guy is shooting up to infinity. So by doing this little rewrite with my x, writing my x as 1 over x, I can now describe this guy before that was 0 times infinity. I can now describe him as infinity over infinity. And because I can describe him as that, I can apply L'Hopital's rule. So how you can say that. Usually for shorthand, I just do this. I just write a little L, comma H over the equal sign here to let you know that I'm applying L'Hopital's rule. And be careful here, you don't apply like the quotient rule or anything. You literally just take the derivative of the top and the derivative of the bottom. So the derivative of ln x is 1 over x over the derivative of this guy is minus 1 over x squared. Now what I would do here is I would simplify. I can just flip and multiply. This actually becomes negative x. And so as x approaches 0 from the right of the function negative x, that is actually 0. So it turns out x times ln x, as x is approaching 0 moving from the right, the limit is actually 0. This is one of the ways, for example, so this, back in Calc 1 they would have told you how functions behave in relation to each other, like the fact that exponentials will go really faster than polynomials, and polynomials will go really faster compared to logarithms, and so on and so forth. And so the idea here is that if you have these two functions battling it out, the polynomial will actually approach 0 a lot faster than the logarithm will approach infinity, and that's why in this case the 0 wins, right? And so you can actually use these laws about limits to actually talk about functions in general, how fast different functions can actually move and produce output. So logs move very slow in relation to polynomials, so usually if you have a polynomial and a log together, the polynomial is kind of going to determine what's happening overall. And we see that happening here as well. So it turns out that this limit is 0, and I could figure that out by first rewriting a little bit to look like one of the forms of 0 over 0 or infinity over infinity, and then I apply L'Hopital's rule. Let's do another example. Okay, so this is a directly like L'Hopital's rule, form infinity over infinity. Let's say I wanted to find the limit as x approaches infinity of ln x over x, or I wanted to find the limit. Well, that guy I mentioned before. So looking at this one, again I can notice that as I plug in x goes to infinity, my log is going to go to infinity, and then that's also going to go to infinity. But you might not be so sure ahead of time which one is going to win, so what you can do is you can apply L'Hopital's rule. So what that's going to give me, I'm going to differentiate the top, which is 1 over x, differentiate the bottom, which is just 1. So that's just now the limit as x approaches infinity of 1 over x, and that we know is 0. So again, that's 0. So if we have a fraction where there's a log at the top and a polynomial at the bottom, turns out that the polynomial will grow a lot faster than the logarithm, even though they're both going to infinity, to the point where the log might as well be 0 compared to the polynomial. Now a similar thing happening here. Clearly the exponential is going to go to infinity and x is going to infinity, so that's infinity over infinity. Here what we can do is apply L'Hopital's rule. So this is the limit as x approaches infinity of derivative of e to the x, we know is e to the x. Derivative of x, we know is 1. So that's just the limit as x approaches infinity of e to the x, which we know is infinity. So among other things, that kind of tells you, compared to x, e to the x is growing super fast, whereas even though both of them are getting huge, your e to the x is infinitely huger than the x. And so that limit would actually be infinity. Any questions on these so far? Are we okay with these? I think once you take L'Hopital's rule on faith, it's kind of okay to see these things. do another example. What about the forms, if I see something like infinity minus infinity, how would you deal with that? Well, it would depend. So let's do an example here. At the limit as x approaches infinity of e to the x minus x. And the limit as x approaches infinity ln x minus x. So clearly here, as I'm going to infinity, my e to the x is going to infinity, as well as the x is going to infinity. So I'm having infinity minus infinity. Now in theory, based on that, we kind of think that this infinity should be a lot bigger than that one, and so if we subtract them, we'll still have infinity as the answer, but let's actually see how we can do that. One way in which I would try to rewrite this one is to actually factor. Let's say we wanted to factor out an x. What would I have left with inside?
E over x, sorry, e to the x over x minus 1.
Minus 1. Now what can you say about that? What is this now approaching? Clearly this guy is still going to infinity. What about this guy?
Going, let's go to infinity.
It's also going to infinity. This guy we saw goes to infinity in the last example. So this guy's also going to infinity. So this is going to infinity times infinity. What is that? Infinity squared. In other words, it's infinity, right? Infinity times infinity happens to not be an indeterminate form. If you take one huge number, multiply by another huge number, the result is a huge number. There's no question about that. That just goes to infinity. Try something similar here. Factor out an x, limit as x approaches infinity, ln x over x minus 1. So now we just check what this approaches. This would approach infinity for the x times, and again in a previous example, ln x over x as x is approaching infinity, I know that approaches 0. So this guy I know will approach 0 by second to last example. And so this approaches 0 minus 1. In other words, it approaches infinity times minus 1. So it's a huge number times negative 1. The result is a huge negative number. So it turns out if you're taking ln x and you're subtracting x, you're subtracting something a lot bigger. The x is a lot bigger than the ln, infinitely so. That was that example. So we kind of applied L'Hopital's rule inside the parentheses here. We already previously did that, so we don't have to do that again. Yeah.
So you can break out L'Hopital's rule to solve a certain part of the overall limit that is indeterminate.
Yeah. Yeah, in fact, you can kind of do that using the limit laws that you would have learned in calculus, like limits distribute across sums, and it had all these other properties that we could apply.
Okay.
So yeah. try these. I'm going to give you some examples where you actually need to repeatedly use L'Hopital's rule. So here's a couple examples of that. Limit as x approaches negative infinity of e to the x times x squared. Limit as x approaches 1 from the right I mean, next time we see each other, starting on Wednesday, we will actually start chapter 7, which I think is a very fun chapter. We're going to learn to integrate we're going to learn some new integration techniques, so we're not just stuck on integration by substitution all the time, and it should be fun. Hopefully I'll be over my flu by then, and I'll be able to be all excited about it. Okay, so what is this approaching? Is I plug in negative infinity to x for e to the x, what does it go to? Well, 0, right? Because e to a negative number is just 1 over e to the positive number, so that's going to 0. So this is kind of going to 0 times infinity here. So what I would do is I actually try to rewrite things a little bit. And so, how do you rewrite this? What do you want to do?
Factor on x squared.
Well, I mean, the x squared is already multiplied, so factoring is not going to really do anything. What I would do is I would do a similar thing to what we did in the first couple of examples and kind of like write one of these guys as 1 over the other guy. So for example, I could do something like leave that as x squared and move the e in the bottom. Just make that a negative power, for example. And so now if I look at this guy, that actually approaches infinity over infinity. Right, because I plug in negative infinity for x, negative times the negative makes it a positive, so it's e to the positive infinity in the bottom, so that goes to infinity over infinity, which now means I can apply L'Hopital's rule. Differentiate x squared, that gives me 2x. Differentiate e to the minus x, that gives me minus e to the minus x. And so now you look at that for a second, and you realize that if I plug in negative infinity, that also goes to infinity. And the e to the minus x also goes to infinity again. This goes to negative infinity over negative infinity. So, which is, again, it's a situation where I can use L'Hopital's rule, so I would do that. So I apply L'Hopital's again. Differentiate the 2x, that gives me 2. Differentiate this guy, get e to the minus x. And so now the top is 2. That's actually approaching 2 divided by infinity. Which I know what that answer is. That's going to be 0. So this limit is 0, which is equal to that limit, which is equal to the original limit by L'Hopital's rule. So 0 is the answer here. And I had to apply L'Hopital's rule twice, but that is completely okay. Because you have this cascading effect. What about something like here? So we know about our ln, it looks like this. We're approaching 1 is where it hits 0 from the right. So that would actually be 1 over 0 plus, so that's actually going to infinity minus infinity. So this is actually approaching infinity minus infinity, so I'm probably going to want to rewrite that to look So what do you think here? What can we do here?
Do we need to make a common denominator between the two to
Like
make it
combine the fractions?
yeah, to make it a full fraction? Or like, so that way we can invert one side. That makes sense.
Sure. And so what would that look like here? That'd be what? X minus 1 minus ln x divided by x minus 1 ln x.
Yeah.
What does that actually approach now then? So as I approach x equals 1, log of 1 is 0, this would be 0, so that gives me 0 on top. Log of 1 is 0, 1 minus 1 is 0, so that's 0 times 0, so it gives me 0 in the bottom. So this is actually a 0 over 0 limit. So now I can actually apply L'Hopital's rule here. So differentiate the top, that just becomes 1 minus 1 over x. Differentiate the bottom, I need to use the product rule. So that's differentiate this first one, leave the second one, plus now I differentiate the ln x and leave the 1 over x minus 1. What are we getting now? So let's check in here. As my x is approaching 1, this becomes 1 minus 1, so the top is 0. As my x is approaching 1, log of 1 is 0. And so now I have 0 over 1, so that's again approaching 0. So let's actually apply L'Hopital's again. But I'll probably simplify a little bit before applying L'Hopital's because I don't want to have to do the quotient rule in the denominator or something. That's going to be kind of annoying. So I probably multiply by x over x. So let's actually look at that first. So approaching 1 from the right, multiply the top by x, I get x minus 1. Multiply the bottom by x, I would have x ln x plus x minus 1. Okay, so that's the same here. That still goes to 0 over 0. So now let me apply L'Hopital's. So now I differentiate the top, that's just 1. Differentiate the bottom, that's going to be ln x plus 1. Because if I leave that and differentiate that, I get 1 over x. Plus that, get 1. So now that's not indeterminate anymore. The top is definitely the number 1. And the bottom, ln of 1 is going to 0, so that just becomes a half. Right, one thing you can note here. There is some virtue sometimes to just taking a step back and reevaluating your position, because you don't just want to just start taking derivatives all the time, because you might end up in a harder situation than you want. Every now and then, after you apply L'Hopital's, you can probably simplify before recognizing whether you need to use it again. And you can. We actually did that here to make our lives easier, because differentiating that denominator is a lot easier than differentiating this denominator. You have a question?
No, I figured that.
Yeah.
So how come we didn't multiply the whole thing by x over x just to bring that 1 over x up? Is that because it was a
Well, that was just force of habit from dealing with complex fractions back in algebra class. When you have a fraction of fractions, you multiply top and bottom by the LCD to simplify it. So that's kind of how I was thinking. But you could actually do something like factor 1 over x for each part, and the 1 over x's would cancel and you'd end up here. There are various ways you could do that. Or you can create a common denominator, combine the fractions here, combine the fractions here, and flip and multiply. You'd eventually get to the same spot. So there are a multitude of ways to actually simplify from this to that. But I think multiplying and dividing by the LCD when you have a complex fraction is one of the quickest ways to actually simplify. Did any of you do examples like this back in Calc 1? You did? Yeah. So it's like one person. Okay. So yeah, so there are a lot more complicated limits that we can do now that we have. So let's look at some examples where we can actually use logs and exponentials to help us out. So look at these examples. Limit as x approaches 0 from the right of sine x raised to the x power. Or limit. This was probably the first example I should have done. X raised to the x power. The limit as x approaches infinity. These are the last three examples. You'll notice that this guy here is approaching 0 to the 0. So is this guy approaching 0 to the 0. This guy is approaching 1 to the infinity. By the way, we know that this is supposed to give us the answer e, so we're actually going to see how that would work here. To show that our rule is actually consistent with what we know the definition should be. So the idea behind this is we're kind of going to do something similar to log differentiation. Remember where we logged both sides and then we could use implicit differentiation to get to a derivative? We're going to do the same thing with the limit. We have like literally a minute left, so let me do it with the easier one so you guys can see. So here's the trick that we're going to use. Because we have a variable and a power, we know that logs have the ability of taking powers down and becoming products, and we actually know how to deal with products. So we set y equal to this limit. And then what we do is we log both sides. Because log is a continuous function, I can take it inside the limit. Because that's a property of continuous functions. And so now what happens is I can use my log rules to simplify that guy a little bit. So that becomes x log x. Now this guy, you'll notice, approaches 0 times infinity. That's actually one of the first examples we did. So the trick here was to rewrite that as ln x over 1 over x. That guy would approach infinity over infinity. So now I would apply L'Hopital's rule. That becomes 1 over x minus 1 over x squared. That guy we actually knew was 0. And so what we can say here is ln of my y is 0, but my y was the limit. So what I can do is I can solve for y, and that was just the e to the 0, which is 1. So that means that my original limit as x approaches to 0 from the right of x to the x, is actually 1. So in that case, 0 raised to the 0 is 1. We'll stop there. I'll see you guys on Wednesday. But that's kind of essentially what you would do with these other guys, just log both sides. The other option, since we won't be seeing each other for a while, just for you to test out The other option was to do that trick where you can rewrite something as e to the ln of itself. So you have e to the ln of x ln x. And you can kind of do L'Hopital's rule with the power of the exponential. You have that option as well.
So what should we just do?
So do the homework for 6.8 and 6.7 and bring that in on Wednesday.
So this is the last part of 6.7, explain.
Yeah, 6.8, these were the last examples. So you kind of know the tricks for them.
And Wednesday we should start integration.